Hi, and welcome to this short instructional video. It's designed to get you started on doing spectral analysis in the TF32 software. As you can see, I've got my TF32 software opened up. I have a sound file loaded. And the first thing I'm going to suggest that you do is to maximize the window of this so it occupies the entire computer screen. And then to open up a spectral display, you go to the View, Open, and select the option Spec. And if you do that, you're going to get an added pane right below the sound pressure waveform, and this is an amplitude spectrum. So we have frequency on the x-axis and amplitude on the y-axis. The amplitude spectrum is generated based upon the location of the left cursor in the sound pressure waveform. As you recall from class, an amplitude spectrum is kind of like a slice in time and shows you the frequency composition of a sound at that slice in time. And so the left cursor is the cursor used to determine where the spectral analysis is going to be performed in the sound waveform. As you can see right here, there's very little energy. It's sort of the energy is down towards the bottom of the plot, and that's because if you look in the waveform, my left cursor is sitting in an area of silence. As I drag this over towards the waveform, you can see that now things are starting to look a little more familiar to you. You're starting to see greater energy in the amplitude spectrum, and in this phonated segment you can see harmonic structure associated with the signal. Now, a common problem that students have is they many times try to do a spectral analysis when they also have the right cursor in the window as well. And so if I introduce the right cursor here, you can see that it has no effect on the spectral display. But as I move the right cursor closer and closer to the left cursor, the appearance of the amplitude spectrum starts to change dramatically, to the point where if we get within, for example, 50 or so, or less than 40 or 50 milliseconds, the appearance of the spectrum looks rather odd and nothing like you would expect based upon what you see in the sound pressure waveform. That is because there is a default window, analysis window, over which the spectrum is generated. And if your left and right cursor are closer together than the size of that analysis window, then it performs the spectral analysis on the smaller window occupied by the left and right cursor. The bottom line is that then it gives you a more not as representative view and as you would expect. And the simple way to solve this problem is just to simply either get rid of the right cursor or slide it far enough away from the left cursor so that you can see the program is allowed to do the analysis over the time window that you expect. The other time where you might have this happen is if you've actually done a super large time expansion of it, and you only have, for example, a window that is showing 50 milliseconds or so of the signal. That will also give you a spectral view that has these different qualities to it due to the very narrow time slice that's being performed. Okay, now that we have our amplitude spectrum as we expect to see, we can also do various kinds of measurements here as well. And so we can introduce a cursor into the spectrum window by simply clicking the left mouse button while you have the mouse in the spectrum pane, and you see a vertical dark line, and that line can be dragged back and forth, and this can be used to make measurements. Alternatively, you can press these two buttons in the upper right hand corner to help um, to, 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 to move your cursor to regions of interest. So for example, let's say that you are interested in measuring the amplitude and frequency of the first harmonic of this particular amplitude spectrum. You can slide this over, and way over to the left here at the lowest end of the frequency range, we can see this is our first harmonic, this discrete peak in the spectrum. And you can try to manually place the vertical cursor on the peak. And if you want to know what the value is of that, you can go over to the upper right corner. There's a small table here. It's got 2 rows and 2 columns. If you look in the first row, there's a number that tells you what is the frequency associated with the location of that cursor, and then what is the amplitude of the signal at that frequency. Notice that the frequency is expressed in kilohertz here, so it's actually 0.094 kilohertz or 94 hertz, and that the amplitude is minus 50.9 decibels. And this amplitude measure, often we don't concern ourselves too much with. We're mostly interested in what is the frequency of that peak, at least for the purposes of our class. And so you can manually measure that. Now, one of the problems associated with doing a measurement this way is that with each successive button push of either this up here or by clicking and dragging, you sometimes can actually miss the peak because the resolution of the screen prevents you from being able to lay the cursor directly on the peak. And so as a result, this software has a really nice option that allows you to automatically find the peak. What you do is you can, for example, if you see a harmonic that you may want to measure the peak of, you click to the left of that harmonic or to the right and simply drag the cursor across that peak. And what it does is that it takes that window that you've passed the cursor through, and the computer automatically looks for the true maximum value there in terms of the magnitude of that and then also what frequency it's at. So if you look up over here now, and that is expressed in the second row of this table, what we see here is that while our hand measurement suggested that the peak was at 94 hertz, this automated measure says that it's at 88 hertz, so it's a little more precise. And so you can do this for any local maximum in the amplitude spectrum. For example, let's slide this across to the right and look at the next peak, the second harmonic. As we pass it through, we look up here and see, lo and behold, it's automatically found it to be 176 hertz. So that's a very handy way to get a more precise measure of a local peak in the amplitude spectrum. That's the end of this first part of this particular tutorial, and there is a second part that will talk about some of the other options.